Ampere's Circuital law. Line integration. When we saw electric field, we have obtained line integration, and that means we took a very small part, then we integrated so that whole can be achieved. And for the magnetic field, this can be done. We can consider electric currents like I1 to I6, as you see here, I1 to I6. All these currents, they produce magnetic field in the region around these electric currents. So a plane which is not necessarily horizontal, if you see here, an arbitrarily closed curve, if you see this red line, a red curve is also shown. So let us take a line integration of the magnetic field on this loop, and there are certain things you need to remember, that we have taken a sign convention for electric charges while considering the surface integral in the case of Gauss theorem for electric field. In the similar fashion, we will have to decide a sign convention for the electric field enclosed by a loop, right? Arrange a right hand screw perpendicular to the plane which contains closed loop and rotate it in the direction of vector line elements taken for the line integration. So electric currents in the direction of advancement of the screw, this we will consider as positive, and the currents in the opposite direction will consider as negative. So now using this convention, if you see this figure, we have this I1 and I2. These two will be negative. I3 and I4 will be positive. So if we have taken a plane and the curve which inscribe this I1 to I4, we can say that the algebraic sum of all these current, that is I3 plus I4, and the sign convention I minus I and minus I2 is sum of the current. And you don't have to worry about the currents which are not enclosed by the closed loop which are selected. We don't have to worry about this or this. So the statement of Ampere's circuit law is what? It says that the line integral of magnetic induction over a closed loop in magnetic field is equal to the product of algebraic sum of electric current which is enclosed by this loop and the magnetic permeability. How can we define, or how can we present this mathematically? This is the line integral of magnetic induction over a closed loop in a magnetic field is equal to the algebraic sum of electric current enclosed by that loop and the magnetic permeability. So the magnetic induction in this equation is due to this current from I1 to I6, while the algebraic sum of current, if you see, is only because of I1, I2, I3, I4, that is the current which are enclosed in that closed loop. If you see here, only these four are being taken. And very important to note that the Ampere law is true only for steady currents, only for steady current. Just as we saw in the static electricity, the electric field due to symmetric charge distribution we can determine easily using the Gauss law. So the intensity of magnetic field due to symmetric current distribution can be determined in the same manner using the Ampere's law. You can say that Gauss law in electricity, or while we are discussing static electricity, is almost equivalent or a counterpart like Ampere law in the magnetic study. So Gauss law for the electric field and Ampere law for magnetic field, they have their own importance. Like the Gauss law and this Ampere law, they form two basic pillars out of four pillars of the Maxwell's electromagnetic theory. The third pillar is what? Is the fact that magnetic field lines, they form closed loops. And the fourth one is the concept of displacement current. Ampere law is the integral form of Biot-Savart law, and Gauss law is the integral of Coulomb's law. So these representations are very important in order to find out that how this magnetic field is related to the current.